we'll directly go to the today's discussion. For the first one, let us take the simplest one. An ideal gas at temperature T1 and P1 is compressed isothermally to pressure. What is it? We are increasing the pressure in a closed system. Which of the following is true? Quick answer panila. We will also give some relevant discussion on that, this aspect. First part is about internal energy change for the ideal gas. Sorry, I'll write the title now, which is about what is it? Delta G and delta U for isothermal compression. Yeah, that is what is the problem we are saying of ideal gas. So what is delta U for this compression process? Any answer, Pa? The simplest answer I'm expecting. Hello. Fine. I should not ask that. Your guess is B. B, yeah?
D, sir. D for dog.
D.
D, sir.
D, B. Okay. Option is okay.
No, sir. D.
D. Everyone is saying D. Say then we have to. I need to give more explanation. I expected A or B. Okay, A, B, better answer, better option. I will tell you that. Tell me.
இப்போ வந்துட்டு நமக்கு ஐசோதர்மலா பிரஷரை இன்க்ரீஸ் பண்ணோம்னா வந்து நமக்கு அந்த சிஸ்டமோட பொட்டன்ஷியல் எனர்ஜி இன்க்ரீஸ் ஆகும்ல சார்?
Pressure increase na potential energy increase. Okay, so there is a
internal energy அதிகமா இருக்கும்.
Okay, அதுக்கு வந்து கொஞ்சம் relevant points நான் சொல்லிறேன் முதல்ல. We'll you have come across with this definition of delta U for an ideal gas, no? So delta U for an ideal gas is simply equal to CV delta T. ஞாபகம் இருக்காது? You know this definition? Like this we also have delta H equal to CP delta T. So what is the meaning of this? Ideal gas at and U for an ideal gas is simply a function of T alone. Like that, H also is a function of T alone, which means the U and U and H won't be affected by any pressure differences. So now using that this rule, of course, this relevant theory we are not going to discuss this. So delta U equal to simply CV delta T and delta H equal to simply CP delta T. Otherwise, delta U and delta H are simply functions of temperature for an ideal gas. So this is applicable only for an ideal gas. Okay, whatever the statement I am saying is only for an ideal gas. Otherwise, it will be added with the another terms like pressure change or volume change. Okay, so we are going to see the another extension of this problem. Otherwise, the first one is the ideal gas, and for non-ideal gas, we are going to see another problem in the next one as the next one. Okay, so using this statement, can you now say which are all correct? A and B are supposed to be correct right now.
Yes, sir.
Say otherwise, U is a function of temperature. Since we have this statement like what is it? Isothermally, yeah. For an isothermal process, T is constant, yeah. So since T is constant, delta U is also constant. So otherwise, U1 and U2 are the same. Fine. Are you agreed about this? No. Either this condition A or B is the correct one. Of course.
Yes, sir. A or B is.
Yeah. Okay. Now we need to choose about this G. So what is a formula available for G? We'll make 1 minute. I'll go to the here. Otherwise, this is about delta. Sorry, I'll use better color. No? Delta G and delta U for isothermal compression of ideal gas. So delta U equal to, I'll use white color, that is much better. So delta U for an ideal gas is simply equal to Cv delta T. Likewise, even delta H is also equal to Cp delta T. Otherwise, they are simply functions of temperature. U and H are functions of temperature alone. So from that, for an ideal gas, with for isothermal process, so delta T equal to constant, or is delta T equal to 0. So from which we have delta U equal to 0, or simply U1 equal to U2. Fine. So now the next one is, I will say either A or B is correct. But again, what is about G? So we know this expression for DG, no? DG equal to VdP minus STT. Are you aware of this expression, Pam? These are all what is called as the fundamental energy relations. Okay. So TG, we will also make a derivation of this in the next one. Next exam, next problem is about the non-ideal gas, which is for van der Waals equation. We are going to do some problem. Sorry. So from this, again, what I said already, it is a isothermal process. Yeah. So isothermal process, dt equal to 0. So we have nice simple expression, dg equal to vdp. dg equal to vdp. So what are all given? Simply pressure P1 to P2. And what about V? Otherwise, so it is delta G equal to. So what do you can write this V in terms of RT by P? No, you can replace this V in terms of pressure. PV equal to RT. This is applicable for ideal gas. No, so this we have not D. This left side is also D. No, DG. DG equal to RTP. We can take delta G, that is equal to RT ln P2 by P1 will come now. Is it fine now? So temperature is remaining constant, so T is remaining constant. Only the P2 is higher than P1. So since P2 is higher than P1, delta G is positive, no? Because ln of P2 by P1 is a positive quantity. So delta G is positive, which means G2 is greater than G1. So what is the condition available? G2 is greater than G1. So your condition B is correct, huh? Correct now? The answer is going to be B. Is it acceptable to you? Fine.
Yes, sir.
Because increase of pressure, simply you can say like delta B is going to increase. Of course, volume you can, if you consider to be constant also, but volume is also a variable. Since volume is a variable, always V equal to RT by P, you'll be having delta G equal to RT ln P2 by P1, and P2 is higher than P1, so ln of that quantity will be a positive thing. Whereas suppose ln of P1 by P2 ln of P1 by P2. Otherwise, in the case of this is compression process, P2 is higher than P1. Whereas for the expansion process, how it will be? The P2 will be lesser than P1. So you'll be having ln of fraction, that will be negative. Fine now. So for expansion, delta G is free energy decreases. That you can. For compression, what is it? There is an increase of energy. What is, of course, free energy or whatever the term. Gibbs free energy is increasing with increase in pressure. So the answer is B. Okay, now I said about doing this kind of problem for non-ideal. So that we are going to see now as the next one. So how much time we spent? About 10 minutes we spent totally so far. We are going to the next one, which is about internal energy change. This also again a isothermal process. It is about finding internal energy change. But here it is said like it is not an ideal gas. It is following the van der Waals equation. No, this is P plus A by V square into V minus B equal to RT. Otherwise, this is not an ideal gas. Only for ideal gas, isothermal process is simply leading to du of 0. But for this non-ideal gas, du will be definitely some non-zero quantity. So let us write the title here, which is about delta U for van der Waals gas. Delta U for, again, this is isothermal process. இப்போ எங்க எப்படி ஆரம்பிக்கிறது? How to start? How to find this du or delta U? So here only we need to have this, all these Maxwell relations. We need to write the Maxwell relations. So எங்க இருந்து ஆரம்பிக்கலாம் முதல்ல? So I said now this mnemonic diagrams are very helpful. I will draw this. 1 minute. Okay, rough diagram only I will make. Rectangle மாதிரி போட்டா நல்லா இருக்கும். Right, square. So we used to do this, no? Of course, I am comfortable in using this mnemonic diagram. So we have this pointing arrows. We can write what is du. Du equal to for u. Say for u, the side variables are p and t. You can write the side variables as such. So you can write the variable as p and t, and the distant variables to t. That is for the distant variable is the side variable and distant variable are connected through this arrows. For the side variable t, the distant variable is s. So t into ds. So the distant variable we mark it as ds. So t ds. And for p, the distant variable is v. So p dv. Okay. So p dv. Again, we need to write the signs and all, sign convention. The sign convention says, so if the arrow is pointing towards the side variable, we need to have a negative. Say for the p variable p, this arrowhead is point. I will write it. So for the variable p, the arrowhead is pointing towards that, so we'll be having a negative. And if it is leaving, or is whatever is given out, that is taken as positive in this numeric diagram terminology. So otherwise, here we have plus. Actually, the relation is simply TDS minus PTV. From the numeric diagram, from what is the original definition of du? From the first law, we have du equal to dq plus tw, and tq will replace with the definition of entropy change, tq equal to tds, and dw equal to minus pdv. You can simply get this way. Otherwise, you can also use a mnemonic diagram and get this. Okay, we are still going to make use of this mnemonic diagram for some Maxwell relations and all. Okay, now what is asked is you want to find delta U for isothermal expansion. So otherwise we need to write this U in terms of what is it, volume. So expansion means volume. Otherwise we need to know about this. The volume data are given. So if U is written in terms of temperature and volume, our problem will be otherwise we'll be having an expression. Sorry, I'm going to write like U as a function of T and V, and we can write this du equal to, we can writing this in terms of partial derivative, dou U by dou T at V dt plus dou U by dou V at T dV. Okay, so we have one equation, this equation available. And here, what is dou U by dou T at V? The definition of from the definition of CV, actually CV is defined as dou U by dou T at V. The U and V தெளிவா போடுங்க. This part is not clearly dou U by V. ங்கிறது ஷார்ப்பா இருக்கட்டும். U. Okay. So what is dou U by dou T at V? That is CV. So we have CV dt plus again this dou U by dou V at T we need. dou u by dou v at t. For getting that, we can make use of this equation 1, dou u by, or is we are dividing this equation 1 with v, dou u by dou v at constant t. So which is t into, since constant t means, okay, the t we won't have any derivative, t into dou s by dou t at v minus p. Service from equation 1, we have obtained this other equation, which is dou u by, we have divided the first equation with v everywhere, with dv everywhere, and applying this partial derivatives. So this dou u by dou v at t, that is equal to t into dou s by, dou s by dou v should be, no? Dou s by dou v at t. 1 minute. There is a mistake here. So if I commit any mistake, please tell me. Dou s by this one, no? Dou s by dou v at t. Otherwise, everywhere we are dividing with v and at a constant temperature. So dou u by dou v at t, and since it is a constant t, you can take the t out. So dou s by dou v at t, and already we have divided this, no? Service, we are dividing this dv and right, using this partial operator. We are dividing this equation by v dv simply. So we have divided it, and we are having this dou u by dou v at t as t into, so we'll use that now, which is t into dou s by dou v at t. It will be taking some time, minus p. We'll spend more time for this problem. Okay, fine. But already we know this, it's isothermal operation. So this part, no, this first part is 0. So we have du equal to t into dou s by dou v at t minus p into dv. But we don't know any information about entropy in this problem definition. Instead, we know about the information about pressure, temperature, volume. So we are going to replace this dou s by dou v at t using Maxwell relation. So how to write dou s by dou v at t? So I'll give an idea about this. We'll take this pneumatic diagram again. So I'll make it here. So we are going to, what is needed is dou s by dou v at t. So we can write a always we are making a box like structure around this. So what are all that? So this dou s by dou v at t will be equal to dou p by dou t at v. Otherwise, we are connecting two verticals. So this is one vertical, this is one vertical. So whenever you connect two verticals, you will be having the same sign. So otherwise, I'm going to write this dou s by dou v at t. Say that is dou s by dou v at t. That is dou s by dou v at t equal to dou p by dou t at v equal to dou p by dou t past gv. Okay, everything is fine only now. Is using that, if you have equation 2, 3, and 4, so using 4 in 3, we have du equal to t into dou p by dou t at v minus p into dv. Okay. So what are all available now? So in the, okay, we have this expression, always we need to have a relation for p and dou p by dou t at v. If you are having that, we can solve the problem, because we are given with some volume data, pressure data, everything. So now let us write this equation, which is what is the equation we have? P plus, I'll write that P plus 360 by V, no? P plus 365 by P plus A by V square, okay. By V square into V minus, what is the B value? B value is 0.043. 0.043 equal to RT. Okay, now we have to rearrange to the form like P equal to, so because we need to get this coefficient dou P by dou T at V evaluated. So we can write this expression as RT by V minus 0.043 minus 365 by V square. So this is the expression for P. We can get this, we can take a derivative of this expression with respect to T at constant V. Otherwise, dou P by dou T at V, we are going to make it. So it's a constant temperature, so T is constant and R is already a constant, and at constant V, so otherwise the first term will be simply remaining as such. So otherwise dou P by dou T at V equal to with respect to T, no? Otherwise 1 minute, I need to look at my. So what will be the dou P by dou T at V? If any of you know, please let me know. Okay, otherwise with respect to T, your otherwise T will be dy by dx. If you have terms of y, sorry. Sometimes I'm stucking up with this derivative. Otherwise, we'll be having this RT won't be appearing. So RT, so that is the derivative of this part with respect to T. So dt by service we have T. If you take dt by dx, service will be having only this constant terms available. So rest we it is simply will be getting as R by yeah, right. So we'll be having R by V minus 0.043. And it's a constant with respect to constant volume means, so this will be this term will be simply 0. So we have this dou P by dou T at V equal to simply the V term we need not consider because it's a constant term. There is a derivative of this expression with respect to T. Otherwise you can also simply take like P by T and take a derivative. So otherwise we have this simply R by V minus 0.043. There is a term and we have to use this in the equation 5. So then using this above in the 5, we'll be having du equal to what are all the final thing? Yeah, this is going to be dou P by dou T at V is simply R by we'll be having this term and minus P. So otherwise we have I need to cancel out certain terms. I say upon combining this, say 1 minute, I will யாராவது கொஞ்சம் சால்வ் பண்ணி சொன்னீங்கன்னா சரியா இருக்கும்பா. சரி, du equal to at last we'll be getting only this term like 365 by V square. So this is where this is where P term I was already having this group, whereas this dou P by dou T is having this group. So these two will be getting cancelled. So dou P by dou T at V is having only R by V minus 0.043. Multiplying this with T will be having this and P. If you take this minus P, at last you'll be having only 365 by v square. Okay, that you can verify yourself. So delta u equal du equal to, we have 365 by v square term already we have, no, v square 365 by v square into dv is available. Yeah, how it is available as dv, because we have the final expression, or is we have this in dv. Okay, now we have the final expression in a simple way. Du equal to 365 by v square into but what is interested, we need to get delta u. Delta u equal to integral of this quantity. So it was 365 into integral of dv by v square. So 1 to 2. So we have minus 365. Y minus is coming, or is v power minus 2 plus or plus 1 by, or is integration of 1 by v square. We'll be having as minus of 1 by v term into v1 to v2. So 1 and 2 volumes are available here. Given problem is the initially it is at a pressure of 1000, there is 1013 kilopascal, and it is going to 1013.32. So the initial the volumes also given. It is expanding from 0.215 to 30.353, 0.215 and 30.53. So you can substitute that volume data for V1 and V2. So we'll be getting this delta U as equal to minus 365 into 1 by, so the V2 and V1. V1 is this V1 is 0.215, V2 is 30.53. So 30.53 minus 0.215. So you'll be getting the answer as 1685.7. Check பண்ணி பாருங்க, kilojoule per kmol. So delta U is in kilojoule per kmol. How to say it is kilojoule per kmol? Because delta U is having the units of, or is U will be used, U is having the units of P and V. Because we have this pressure and volume usage. Pressure is in kilonewton per meter square, kilopascal. Kilopascal, otherwise kilonewton per meter square. Kilonewton per meter square. Whereas volume is in meter cube per kmol. Meter cube per kmol. So what is the final answer? It is going to be in kilonewton meter by kmol. So there is nothing but kilojoule per kmol. So we are not given with the unit of delta U directly, whereas delta U is involving in terms of pressure and volume data. That is a final expression. So here volume is in meter cube per kmol, and in the pressure also we are dealing in terms of kilopascal. So this multiplication of PV is also having the units of U. So to write the unit is similar, delta U's unit is similar to that of delta PV unit. So P is in kilonewton per meter square and V is in meter cube per kmol. The multiplication, of course, this is an energy term, PV is energy term. So the multiplication is coming in terms of kilojoule per kmol. So otherwise, that's why we are fixing the unit to kilojoule per kmol. So the final answer is this one 1685.7. Maybe I can also check in the. You can also check this in the in my book itself directly. So this was asked in 1996-27. Of course, during that time, they were giving this kind of problem as some 5-mark question. 5-mark question, or they were having this. That 5-mark questions are similar to that of the current 2-mark questions. Okay. In this recent days, they are giving this numerical. You are supposed to enter the answer in the this text box. Whereas earlier we are giving this answer in this paper, and they will be correcting this paper manually. Okay, the summary is, if the problem were an isothermal process with an ideal gas, simply delta U equal to 0. Sorry. Oh, it is 8:20 alarm. I don't know. Okay. So for an isothermal expansion with an ideal gas, delta U is simply equal to 0. That is what's the previous discussion. Whereas now this problem is delta U with a non-ideal gas. For a non-ideal gas, U is not only a function of temperature, it is also a function of volume. Of course, you can also write U as a function of temperature and pressure as well. But normally we will write some meaning, we will get some meaningful expression if you only deal with U as a function of T and V. You can also write this as any for a pure component system or a single component system. The variable of importance, there is output variable, depends on two inlet, two variable of importance. Say otherwise this is coming from the degree of freedom, like F equal to C minus P plus 2. No, single component and single phase, we have 2 degrees of freedom. Otherwise, a variable like U, we can consider like T and V or T and P or whatever the variable of importance. Normally, we'll try to consider this as a function of T and P, because the T and P variable are more readily available, but not always. Again, say U will be considering as a function of T and V. For H, we will be considering as T and P, and for G also will be considering it as a function of T and P. Normally this G and variable, the variable G is mostly used in chemical engineering, and also the variable H is also mostly used for the flow processes. So this U and A are rarely used, but since this first law is based on U, we'll be having this more derivations with U as well. Okay, what is called as internal energy change. Okay, to quickly summarize, so what we did, we have obtained, we have this fundamental energy relation with du. You can obtain this energy relation simply from first law, which is dq plus dw. dq is replaced in terms of entropy change. This is from second law. No? From second law, we have this expression dq equal to tw, and the definition of work dw equal to minus pdv. You can write this way. Otherwise, also you can make use of this kind of mnemonic diagram for writing du. Otherwise, we are having this box-like structure, and PASGVHTU. Otherwise, PASGVHTU. PASGVHTU. We will write a diagram like this. Then we'll have this. We can have this du. For every energy variables are on the sides. For this every energy variable, you can get the expression in terms of this pressure, volume, temperature, and entropy using this representation. Say like for U, the side variables are P and T, and for the T, the distant variable is S, and for P, the distant variable is V. Otherwise, the side variables are appearing here around this U, or suppose you want to write for H, you have the side variables here, and the distant variables are say for P, the distant variable is the distant variable and the side variable are connected by this arrow line, and for T, the distant variable is S, and T ds. That is the distant variable will be having this D term, T ds and P dv. And the sign convention is wherever it is arrow is pointing towards, we'll be having negative. So for for P, the arrow is pointing towards, so we have this negative symbol. For T, arrow is pointing outwards, so we have positive. So in this way, you can also write for other variables. Maybe that practice is given in that two problems already discussed, available in the YouTube channel. Okay, from that from that mnemonic diagram also we can get this the expression for du, and of course fundamental energy relations you can also derive without referring to the diagram from the definitions of the properties. No, We can also write the definition of H, which is equal to U plus PV, and we can write for du and PdV and VdP. From that, we can get the expression for dGATs. But most of the time, instead of making that lengthy derivation, we can make use of this mnemonic diagram for getting these energy relations as well as the Maxwell relations. For example, here we have this Maxwell relation. Which one? This dou S by dou V at T is available, which is written in terms of dou P by dou T at V. Say otherwise, dou S by dou V at T equal to dou P by dou T at V. So we are connecting two verticals. Dou S by dou V at T equal to dou P by dou T at V. Suppose you are connecting horizontals and top. That is, the problem is like dou P by dou S at V, that is equal to dou T by dou V at T. Of course, we have top and bottom are connected. We need to have a negative. So otherwise, I will write this simply. Of course, though it is not relevant to this problem, sometime recollecting this derivation is also good. So I am going to write this connecting this is dou P by dou S at V, that is equal to dou T by dou V at S. Since we are connecting top and bottom, we need to have negative. Otherwise, this one dou P by dou S at V equal to dou T by dou V at S. We need to have negative sign. Dou P by dou S at V is equal to minus of dou T by dou V at S. Okay, that way, of course, this numeric diagram will be very convenient to get these Maxwell relations as well as this fundamental energy relations. Okay, now we have this fundamental energy relation. We also have this. We can also write this U as a function of T and V, from which we have this partial derivatives, and this dou U by dou T at V is simply zero. Simply CV. And this is zero because of isothermal process. So we have only these things to be looked into. And dou S by dou V at T, dou S by dou V at T. Otherwise, we don't have the information about entropy change in the problem. So we can write this dou S by dou V at T in terms of pressure PVT relation. So dou S by dou V at T. So dou S by dou V at T, that is equal to dou P by dou T at V. So using that, we have this final expression. Now everything is only in terms of pressure, volume, and temperature. The final expression is only in terms of pressure, volume, and temperature. We are given with the information about volume change. Of course, before that, we need to get this derivative. For this, we are given with the expression of P as a function of T. Take the derivative of this with respect to T. So you'll be having simply R by this thing. The other things are 0. We have dou P by dou T at V is simply this quantity, and substitute this back in this expression, and at last we have only dV available. That is that we have du equal to this 365 by V square, from which at last we have this expression for value estimation of delta U this way. And we are checking this unit whether they are what is the unit for this. So the unit of this delta U is in terms of this PV. P is in kilopascal and V is in meter cube per K mole. So at last they are supposed to be kilojoule per K mole. Okay, so there is a recollection of this problem. Now let us go back to the other maybe another 3 problem we can try definitely. So in comparison, okay, the first one, this was very simple, which is finding delta U and delta G. The second one is about delta U, which is also having connection with the previous problem. Both are isothermal process. The first one is about ideal gas. Second one is about non-ideal gas. Okay, so now we are going to again ideal gas problem with TS diagram. TS diagram for an ideal gas. 1 minute. So the slope of constant volume line for an ideal gas. Slightly involved, but we can do this. Again, we'll make use of our Maxwell relations and all. Slope of constant volume. Let us first see what is a TS diagram looking like? How does the TS diagram is looking like? So we will go to the here. Okay. This is about slope of. I'll write that. No problem. The height. Slope of constant volume line. Constant volume in TS diagram. So TS diagram first we'll try to represent. Maybe TS diagram for any pure component will be like this, but for ideal gas we are having somewhere in this region beyond the critical point. So at least we are in this region somewhere here. We want to get the we need to compare the slope of this constant volume line with constant pressure line or constant enthalpy line. So what is the meaning of slope of constant volume line, which is about dou T by dou S. That is a slope, no? That is dt by ds we want to get. So always we need to have a relation. I will write this with white color, much better. So dou T by dou S at constant V. We have to compare this with dou T by dou S at constant P. The slope of constant volume line, how it is compared with constant pressure line or constant enthalpy line, which means dou T by dou S at constant enthalpy. So you want to get these values, then only we can say about the slope, how it is, which one is higher or which one is lower. So what are all the formulas applicable and how to write this? So we need to know dou T by dou S at V. So what is this dou T by dou S at V for an ideal gas? So we know this definition of we know the definition of ds equal to dq by t. So from which ds at constant volume equal to dq by t at constant volume. What is dq at constant volume? Which is equal to cv dt. Otherwise we have dou s by dou t at v. So is using this expression, we are saying like dou s by dou t at v equal to simply cv by t. The same way, you can also write this ds as equal to dq by t, and ds at constant p equal to dq by t at constant p, which is equal to dq at constant p. What is dq at constant p? Which is cp dt. Yeah, there is a definition of q. Q at constant p is simply cp delta t, and q at constant v is simply cv delta t. So from this, we have dou s by dou t at p. So dou s by dou t at p. Sorry, already here this t is missing. dq equal to cp dt. So we have ds equal to cp dt by t. So we have cp by t. So these two expressions are available. Using this, now we can say about the slope of constant volume line and constant pressure line. So what is the meaning of slope of constant volume and constant pressure? So the diagram is TS diagram. The slope is simply equal to slope of this diagram is dou t by color. I will change that. So the slope of this is simply dou t by dou s or dt by ds. So this the TS diagram and slope means dou t by dou s. So what is available is now dou s by dou t. Or if you can simply take an inverse of this, we'll be having dou t by dou p equal to dou t by dou s. So dou t by dou s at constant p equal to t by cp. Yeah. Or we are using this expression. Likewise, by using this dou t by dou s at constant v, will be equal to T by CV. So now we need to compare these two relations only. So what is asked is slope of constant volume line, whether it is higher than constant pressure line or lesser than or more than. And the other one is whether this constant volume slope is less than or equal to that of constant enthalpy line. So we also need to make a derivation for constant enthalpy line. So before that, let us finish this part. So otherwise, constant volume line is having a slope of T by CV, and constant pressure line is having a slope of T by CP. And you can easily say which is higher out of these, because we know CP by CV is greater than 1 for ideal gas, no? Or CP is higher than CV. Since CP is higher than CV, 1 by CP will be lesser than 1 by CV. Yeah. So CP is higher than CV. So 1 by CV is higher than 1 by CP. So otherwise, this is higher. Is it okay, Pa? Some response? No, for a long I am only doing saying.
Yes, sir.
Fine. So we can say that this dou S by otherwise which one? Dou S by dou T at V. Otherwise, constant volume line is having a slope of T by CV, which is higher than T by CP. T by C, dou S by dou T by V is higher than dou S by dou T by dou S at V is this is dou T by dou S at V is higher than dou T by dou S at P. Correct, no? So dou T by dou S at V is higher than, the slope is higher than the constant volume slope is higher than constant pressure line. I'll write this. First, the A is not valid because the slope is, it is set like slope is lesser than constant pressure line. They are getting the slope is higher than constant pressure line. So B is correct. But how about C and D? We have to check that. So we need to compare that with constant enthalpy line. So adu poradhukku munala we'll see the plot of this nice plot. This is a plot TS diagram. This is a TS diagram for water. But we are asked about ideal gas. Say even this steam also you can consider ideal gas at T higher than the critical T, and also P lesser than, in this range. In this range, the ideal gas equation is applicable. So in this range, the range at temperature should be higher than, and pressure also should be lower. So this range is very applicable for, in this range we can consider this water vapor also to be an ideal gas. So let us see about this constant pressure and constant volume lines. So the constant pressure lines, either constant pressure line, volume line. So we have in the two-phase region, we have this horizontal line. No, actually they are the pressure lines. Where is that pressure? Say these are all the pressure information. These are all 100 kilopascal, 0.2 kilopascal, 100 megapascal, 0.2 megapascal. So this 0.2 line is going up to here. So this is 0.2 megapascal. This is 0.1 megapascal. So these are all these dark lines. The black lines are constant pressure lines. Likewise, they also have this constant volume lines. Say somewhere here they have marked the constant volume lines. Say for example, these green colored lines. No, the green color lines are actually constant volume lines. The first one 50 meter cube. After then, so the values are noted here. This one corresponds to 50 meter cube per kg. This one corresponds to 20 meter cube per kg. That is the green lines are constant volume lines, and black lines are constant pressure lines. So let us compare at a point. Say at this point, we have the lower black line is constant pressure line. This line is constant volume line. So constant, what we said, constant volume line is having a slope higher than constant pressure line. Correct, no? Or if this is experimentally also coming to the in the same line. say at a point, say at this point, the slope of this constant pressure line is here and the constant volume line is there. The constant volume line is having a more slope than the constant pressure line. Okay, next one is about what about the enthalpy line? How about constant enthalpy line? In this diagram itself, they are giving this constant enthalpy lines by this red colored lines. So the red color lines are actually constant enthalpy lines. In the constant enthalpy line, the slope is actually 0 in the gaseous region. That is the slope, no? This is the slope of constant enthalpy lines. They are appearing as a horizontal lines, which means slope equal to 0. Let us check how our equation is coming for constant enthalpy line. But slightly, we need to again make a derivation. Maybe or I will directly check at my book content. 1 minute. I will directly go to my book and check the problem. How to get the expression for constant enthalpy line. So the problem is this was asked in XC Engineering Sciences sometime in 2009. XC 2009 V7. Simply I am going there. I will give an explanation. No problem. I will first see the solution and come to that. Okay. Yeah. Say the derivation is also simple here. So we want to get the expression for, or what is the expression needed? We want to get dou T by dou S at constant constant H. So this is what is needed. So that is, so far we are seeing dou T by dou S at P and V. We are now extending that to at constant H as well. So the relation for H is available by this way: dH equal to VdP plus TdS. How this is obtained? Again, from I'll write this pneumatic diagram and explain again. So what is the diagram? Pass GV HTU, pass GV HTU. So what is DH? DH for the variable H. The side variables are T and V. So T side variables are written as such, and distant variable for T is S. So TDS, and for V, the variable is distant variable is P. So VDP. So both are pointing outwards. So we have positive. So always DH equal to VDP plus TDS. Okay, this is one expression. But what is needed is we need to get TS and at constant H. So otherwise we need to get we have already this S available here. If you can divide this expression with T, no? We will be having dH by dt equal to VdP by dt. Of course, we are making some additional steps because somehow we want to get dou T by dou S at H or dou S by dou T at H. The reverse also fine, no? ds by dt. Okay, this is a fundamental energy relation for H, and we have divided that expression by dt. So we have dH by dt equal to VdP by dt minus plus T is that, no? TdS by dt at constant H. So left hand side is 0. So we have 0 equal to V into dou P by dou T at H plus T into dou S by dou T at H. So what is needed is this one, dou T by dou S at H. Otherwise, the inverse of this is needed. So we can rewrite this as T into dou S by dou T at H equal to minus V into dou P by dou T at H. But okay, we can take the inverse of this and write this in terms of dou T by dou S. That is what is important. So we can rearrange this again to the form like T into dou T by dou P at H. That is, we are taking this side and this other side. Okay. T into dou T by dou P at H equal to minus V into dou T by dou S at H. Okay. Now we have this. Now, for an ideal gas, actually this is what is called as change in pressure. How does it change? Temperature changes. What is called as for at constant H. This is what is called as for a isenthalpic process. The left hand side is for a isenthalpic process, and we can also say like for isenthalpic expansion or isenthalpic compression. How does the temperature change? This is what is called as the Joule-Thomson coefficient. Joule-Thomson expansion is about allowing expansion by a irreversible way at a constant enthalpy manner. So for constant enthalpy process, constant enthalpy expansion process, how does the temperature changes? For a ideal gas, the Joule-Thomson coefficient, or is JT equal to 0, or is mu JT. We'll write like mu JT is the Joule-Thomson coefficient, which is nothing but your dou T by dou P at H. For a ideal gas undergoing expansion in an isenthalpic process, this temperature change is 0. So otherwise, say for a ideal gas, this dH is a function of T. Since H is a constant, T is also a constant. That is, we are saying in the other way. In the previous problem, we said about temperature and pressure are simply, the enthalpy and internal energy are simply functions of temperature alone. Since enthalpy is a constant, temperature is also a constant. Otherwise, this dou T is a 0, 1 for ideal gas. So otherwise from this condition, we are taking this equal to 0. So otherwise, dou T by dou S at H equal to 0. So this also applicable from the this also seen from the diagram. So here we are seeing that. So this red curves, red curves are nothing but the isenthalpic lines. How do we say it is isenthalpic? Because these are all the enthalpy lines, constant enthalpy lines. Constant enthalpy lines after about 2600, the values are written here. No? So these are all the constant enthalpy lines, and these are all the gaseous region. In this region, you can treat this water to be an ideal gas. So in that regions, you can see that the slope path simply 0. This is the experimental proof, whereas this is the relation underlying theoretical relations. So from the theoretical relation or from the experiment, we are seeing this to be equal to 0, whereas this dou T by dou S at V or dou T by dou S at P, they have a positive quantity, and this dou T by dou S at V is a positive quantity, whereas the constant enthalpy line is having a slope of 0. So otherwise, this constant volume line and constant enthalpy line are never equal, because this is some positive quantity which is equal to Cp by T, which is equal to there is T by Cp for constant pressure, or T by Cv. T by Cv is a positive quantity, whereas 0, or is in comparison to 0, it's a positive quantity. Otherwise, this dou T by dou S at V is greater than dou T by dou S at H. That is, constant enthalpy line is having a slope of 0, whereas constant volume line is having a positive slope. So the constant volume line is having more slope. We don't have any such option. We are having an option like less than or equal. Both are not valid. So only this is the valid one. Of course, it is only a 1 mark problem. We need not have this much of calculations. Simply based on this Cp and Cv values, you can easily say about the slopes. Still, this discussion may be helpful in understanding any other problem as well. That's why we are making elaborate discussion. Okay, we have how much time left with? Another about maximum 5 minutes. Maximum 5 minutes means I can solve only one simple problem. Let us see. Maybe I'll try this one. This was asked in 2017. as a 2-mark problem. Let me see how many of you are still available. Okay, people are available still now. Okay, now what I'm going to do, we are going to find this change in molar Gibbs free energy of the liquid. So what are the this is about delta G of liquid for isothermal compression. Okay, we are again dealing with isothermal process. So what are the equations available? We'll write it quickly. Maximum another 5 minutes. Please remain me after that because I have to join with invigilation to T. Okay, dg equal to vdp minus sdt. Fine, no? This is one expression. But here it doesn't say anything about this data, no? What is it? Isothermal compressibility. Using this data, or for using this data, we need to have expression in terms of the beta, kappa, something like that. I suppose you have this expression dv equal to, dv by v equal to beta dt minus kappa dp. But you check it. Actually, I'll write the correct the left hand side. 1 minute. So because of time pressure, we are going at a faster way now. So this dv by v equal to beta dt minus kappa dp. This is one expression, and this is the expression for dg. And using these two, now we are going to solve it. And it is already said like isothermal process. So isothermal means we can simply take this 0 and these are all not needed. So now we have dg equal to vdp and dv equal to minus, or we can write like 1 minute. I'm going quickly. dv by kappa equal to, or minus dv by kappa equal to vdp again. So this from equation 1. So from equation 1 we have this, and from equation 2 we have this expression, which is dv by minus kappa equal to vdp. So since both the sides are, this is your 1 and 2 and this is 3. So I'll go back to this. So this is your 4. So you can equate 3 and 4, from which we have dg equal to minus dv by kappa. So otherwise, what are all available now? So we are given with molar volume change and isothermal compressibility, which means kappa is available. So otherwise, delta G equal to minus delta V by kappa, provided kappa is a constant. So also they say like kappa is isothermal compressibility, which can be assumed to be independent of pressure. Otherwise, kappa is said to be a constant. So we need to simply substitute the values of delta V and then get the value of delta G. So this I will quickly give the answer alone. You please try yourself sometime later. And with this, we are going to finish today's class. So this is about 2017-32. Please work out. As I said, no, you can try yourself. 2017-32. I'll check the answer and give you the answer. So answer is coming as 2450. Which is coming in Newton meter per mole or simply joule per mole. So what is asked is, you are asked in Newton joule per mole. So this answer is equal to 2450. Okay, try this simply. Always we have used this fundamental relation for Pg, and we are using this equation of state for the liquid phase. Always we will normally use this V as a function of T comma P, from which dV equal to dou T by we can write this dV as dou T by dou V at T into dV. So this expression is coming that way. Okay, and using these two expressions, we are now writing dG as change in volume by isothermal compressibility. And since the other values are available, they are solving it. So only very limited calculations for 2 marks. It's a nice problem, provided you need to connect these two expressions. Otherwise, people won't easily get this idea. But whenever you are given with a data of compressibility or expansivity, always make use of this expression. Okay, then you will be easily getting some relation and you can solve them. Okay, pa, I'm stopping as such now. And any of you have any doubt, we can have get it clarified in the future sessions. Okay. Or else we could discuss